All right, you're with me now. So now we're jumping down to chapter 12. I mean, if you look at your book, there is so much information. Man, I don't want to be 13 again. Anyway, there's maybe it's when you start to go senile, your voice cracks too. Anyway, um, there's so much information. That's why I'm telling you the types of problems to look for your upcoming exam, okay, and to practice. All right, so basically we're talking flow rate here, okay, and notice when you take Q, you got a volume over time, which is you take the volume, the area times the distance that something is traveling. So that's how fast this fluid is going through here. It goes through this distance in a certain amount of time. So you got area times volume, or area times the velocity, which comes out to be volume over time type thing. And due to conservation of energy things, the flow rate of one is equal to the flow rate of another, which leads us to the Bernoulli equation. Once we get down to the Bernoulli, here's Bernoulli's equation, the net um, change. In other words, if we keep the work done is equal, we already know that the work done is the change in speed, or the change in is equal to the change in kinetic energy, which is what they're showing us here. All right, and then due to conservation of energy, P, here it is. Here's the key equation right here. P is equal to P1 plus 1/2 the density of the air, which is what we're going to be using. All right, so let's just go to your homework problem. This is going to be risky. Let's just go to your homework problem here. And yeah, that's where I was looking at. Okay, are you sure CC's is? Oh my goodness, I was having a heck of a time with my ninth grade chemistry of physical science that I took from Mr. Carney in Liberty Junior High back in 1974 and 75. Anyway, oh, this is Professor Rick's playground. This is where I kind of goof around to try and find maybe exams. Oh, first of all, I did this to you last night. We are not going to do homework 13. So let's do this. So let's do this. Physics 210. Here we go. Why don't we delete this assignment? That would be a good thing. Delete. Yes, I do want to delete that assignment. I hope none of you were working on it. Now that's gone. So now let's go here and let's take the assignment. Take it. I want you to take it. Take it like a man. All right, so here we go. Let's take a look at this. All right. A frequently quoted word in aircraft design is that the wing should produce about 1,000 newtons of lift per square meter of wing. Okay, so that's, I worked out a different problem for you all, but that's basically what we're going to. So in other words, you got 1,000 newtons of lift per square meter of wing. So let's take a look at this. That right there, what they told you, and 57 meters per second is V1. All right, great. Okay, so here's what we got. Here's the way your problem. So here's the Bernoulli equation. It's based on conservation of energy. We're going to say the heights are the same. All right, and what they're telling us is, so if the heights are the same, then we've got P1 plus 1/2 rho V1 squared is equal to P2 plus 1/2 rho V2 squared. Okay, and we need to find V2 squared. And what they're telling us, here is what they're telling us, okay? Here's what they're telling us. They're telling us that the P1 minus P2 is equal to 1,000 newtons per meters squared. Okay? That's the coefficient of lift. Or well, kind of. It's a coefficient is kind of sort of. Okay? And so we're going to set this as equal to delta P is equal to F over A. So if I know the square, in other words, I know what force I need. So let's say, in fact, I looked this up. The Airbus, the biggest Airbus. Look at this, 842 meters squared. That's its weight. So how much force is going to be needed? Okay, how much force is going to be needed to get that thing up in the air? All right. So you keep this at, so this is going to be 1,000, and then, so here's what we do. Then the change in P, so the force is going to equal change in P times A. The pressure differential, because what's going on? What's going on? V1 is going underneath, it's going slow. V2 is going over the top, it's going fast, and it's creating a lift. It's creating this change in pressure. This pressure, Mother Nature's trying to close that pressure differential, which is causing this force over the area of the wing. All right, so for an Airbus, you got 842 meters squared, and so they wanted it at 1,000. Look at this lift that's required for that thing. 842 times 1,000. Oh my gosh. 842,000 newtons of lift. If I divide that by 9.8, yeah, 85, yeah, that's about 86,000 kilograms. That's how much force you need. Now, how do we get that change in pressure? Well, our takeoff speed is V1. V1 is takeoff. All right? I'm getting way too deep in the weeds here. V1 is the takeoff speed. But look what happens. Look what we're doing here. We've got changing, we're trying to solve for V2 in this problem. And this is where I kept getting messed up, because P1 on the bottom is greater than, slow moving air has more pressure than fast moving air. So we've got change in P, which they gave us, plus 1/2 rho V1 squared, which they gave us, is equal to 1/2 rho V2 squared. How hard is that? If this is known, then you can find V2 without much trouble, right? All right, good luck.